Today we're doing section 3.5, day 2, and we're going to be discussing Newton's law of cooling today. So the first problem is not Newton's law of cooling. We'll get into that in the second half of the video. So here it says the function f of t equals 30,000 divided by the quantity of 1 plus 20e to the negative 1.5t. Describes the number of people f of t who have become ill with the influenza t weeks after the initial outbreak in town with 30,000 inhabitants. So influenza kind of means like your flu or some kind of illness. So letter A says how many people became ill with the flu when the epidemic began. So when the epidemic began, no time has gone by, so t would be equal to 0. So I have 30,000 over 1 plus 20e, and it would be raised to the 0 power because negative 1.5 times 0 is equal to 0. Anything raised to the 0 power is equal to 1, so now this becomes 30,000 divided by 21, which will equal 1,428. Well, 0.6, so we'll say 1,429 people were sick when it first broke out. Letter B says how many people were ill by the end of the 4th week. So easy enough, we just plug in t equals 4. So I have 30,000 over 1 plus 20e to the negative 1.5 times 4. Calculator work, type this all in the calculator. I would just recommend putting extra set of parentheses in the denominator or do it in 2 stages. When we do this, we get approximately 28,583 people. Again, when we're talking about human beings, we're not going to leave it to a decimal. We're going to round. Letter C says, what is the limiting size f of t of the population that would become ill? So the limiting size would be our numerator. Sorry about that. Because that's how many people live in the town. So you can't have more people sick than are the amount of people that live in the town. So that's kind of like a common sense problem. All right, so now let's get into Newton's law of cooling. So Newton's law of cooling, the formula is T equals C plus T naught minus C times the quantity of E raised to the KT. So just to do some labeling here, we know T is time. Again, there's that K value, so K is going to be a constant value. It's different for every problem. It depends on the information. C is the temperature of the room, or if you're outside, it's what we call our constant temperature. So it's the temperature that is not changing in this scenario. This would be the initial temperature of whatever we're talking about, whether that be cake or coffee or pizza, whatnot. And this would be the ending temp after time has gone by. Okay? You will not have to memorize this formula. I will give you the formula. However, I will not write what all the words and all the letters mean. You have to know that part when it comes time for a test. So letter A says a cake removed from the oven has a temperature of 210 degrees Fahrenheit. That would be our initial temperature. It is left to cool in a room that has a temperature of 70 degrees Fahrenheit. That's our cooling temperature, or the constant temperature of the room. After 30 minutes, there's our time, the temperature of the cake is 140 degrees. That's our ending time. So we're going to plug this in, and our objective is to find what K is, so that way I have a model that matches this exact scenario. So I have 140 equals 70 plus 210 minus 70 e to the k times 30. Okay, so we're going to start by subtracting this 70 over. So I get 70 equals 210 minus 70 is going to equal 140 e to the 30k. Again, common mistake is that students think that, let me change the color, think that this 70 and this 70 just simply cancel. Not true. Again, this is attached by multiplication over here, so you cannot break your order of operations. I'm going to divide by 140 to get my base of E by itself. So when I do that, 70 divided by 140 is equal to 1/2. And now we're going to put this in exponential form. And we're going to use our calculators to get a natural log of 0.5, which is negative 0.6931, equal to 30k. Divide both sides by the 30. And our k value is going to equal negative 0.0231. So this is now the k value that we're going to use for all the problems. So you're going to take out the ending temperature and you're going to take out the time. And then the rest of the information stays. So the starting temperature and the temperature of the room are not going to change. So for letter B, the equation would be T equals 70 plus 140. So you can write 140 because the starting temperature and the temperature of the room is never going to change. So you can go back to writing that just as 140. E to the negative 0.0231. And our time is now 40, so I'm going to plug in 40. Notice no solving is required. It's all calculator work, so you're going to just type it exactly as you see it. And the temperature we get is 125.6 degrees Fahrenheit after 40 minutes. So last one we need to do is letter C, and the process for letter C is almost identical to the process for letter A. The only thing that's different is the ending temperature is now 90. So I now have 90 equals 70 plus 140 e to the negative 0.0231 t. Subtract the 70 over, and we're left with 20 equals 140 e to the negative 0.0231. That's an obnoxiously big point, sorry for that. Divide by 140. And we get 1 over 7, so we can reduce this to be 1 over 7 equals e to the negative 0.0231 t. Putting it in natural log form, and we're going to take natural log of 1 over 7 using our calculators. We get negative 1.9457 equals the right side. We're going to divide by negative 0.0231 to both sides, and we end up getting t is equal to 84 minutes. So again, letter C and letter A, identical process, just different numbers for that. All right, that's all for today. We're going to do a lot more practice on Newton's law of cooling tomorrow.